Anyway, it is people come, we will just see what we are looking for. We are at the topic of current sources and sinks, and we have said that in a CMOS analog IC, a current source or sink acts like a basic building block, and there are three major requirements come from them. One of them is that the output impedance should be very high, as high as possible. Also we must guarantee that all devices are in saturation, and also finally the mirror should satisfy another limit, which is essentially because the good source should have V minimum, that is drop across current source should be as small as possible. So based on these requirements, we already looked into a simple current mirror, okay, and we also looked into the variation in parameters, particularly we looked into beta, Vt and lambda. Generally lambda parameter variations are very small, so they need not be taken every time, but for the completeness we did take that, and based on that we realized that if I want to reduce the percentage error between the mirror source and the output current, then I must somehow manage variations as small as possible. But there are two terms, one positive, one negative, so try to compensate them. Okay. Is that point clear what I said? So here is that word what I am saying, the expression which we have derived. Oh, there is something that day maybe I made mistake, but you can check it yourself again. I have a feeling that I think instead of 2 below the denominator in my expression, it is in 2 in numerator. So this 2 should have something like that, some error is, do not look this expression, look, of course there is a power to the power 4, leaving all higher order terms, this is what typically you will get. And I said to you that these are the two terms which are essentially governed by delta Vt by Vt, and there is a term which is delta B dash by B dash. So if I want to make this as small as possible, these two terms must be very close to this term. Is that clear? So if that happens, probably you will, so you can adjust your lengths, widths, you can also adjust VGS, you can adjust Vt if possible, and then you can minimize the effect of variations. So there is, in case you need a very strong source with no variations, one possibility that we can play with the parameters so that can be minimized. Of course 4% error is normally acceptable in most cases, but in case it is lower than that you require, then you must somehow try to see whether we can minimize that. Delta f is a function, any of them, Vt or alpha or beta or lambda or whatever it is, okay. If any of the variation is 5%, then we find typically this is 4% error appears. Is that okay? You can see this is getting subtracted, so it will be less than major error which is coming, okay. Okay, so this is what we did last time. So today we start with, as I say, one of the features of good current source or mirror, it should have high impedance and it should have low V min, okay. These are the two major features I want to attain, and for this I will start looking into alternative to simple mirrors, and here is the first alternative. We anyway know very well that if you use a cascode, what do you improve? The output resistance. So the one of the feature of a current source was you need a output resistance higher, so use a cascode part there, so automatically R may actually go high, R out should go high. We are also looking for minimization of this, so we see that how much V min we get. V min means at the output what is V min you are actually going to get, somewhere here, okay, and we will figure it out how much is the actually minimum drop across the source which is allowed. So for example I have said a typical for a 5 micron process which is given in Baker's book, say VTN of 0.83 volt over voltage of 0.37 volt, that gives VGS of 1.2 volt. Okay. Please remember VA is VGS minus VT, if VT is 0.83 and if this is 0.37, VGS has to be 1.2 volt. Now We want to figure out what is the minimum drop across the current source for this data, some numbers since we are going to calculate. I thought I should put the numbers. This is taken from Boyce Baker Lee's book data, so please check the numbers if there is something mischief I made, hopefully not. So I am trying to now use a cascode mirror in which I have two stages, you can see from here, M3, M4 forms a pseudo mirrors and M1, M2 also form a mirror kind of structure and one is sitting over the other. But if you look at M2 and M4 and if this potential for AC is 0, this acts like a cascode to that series gate connected to the driver, is that clear? So we are trying to see that because of M4 sitting over M2, at this point the output resistance should be GM times gain plus into RO, okay. So that little more, but that is the typical value. So if I can get that value, then I have improved my current source requirement, R out should be higher, that possibility exists. Now we can see from here the way it is done, this is a current source which we will actually put it through some p channel device later, which is called the bias current, which is our reference current. Since this potential D3 and S3, VDS3, since I am connecting something like this, the gate of this VGS and this VGS is same. Since I am connecting something like this VGS and this VGS are also same. Is that okay? However, please remember some fun part in that this VGS has something to do with drop from here. The source is not now at ground potential for this, source is at drop VDS across this. So VGS may be same, but the source is not at ground, this has to be understood. So the gate voltage is not exactly at the ground for the upper ones, this potential, and it is plus something is adding up, but net value of VGS has to be same if the currents are to be same, okay. So this idea that what will these two do and what will these two do can be figured out from an example given to you. This is still a good current source, there is nothing much you can do analysis, but what is interesting to me is these G's are only written to prove which is gate for one and drain for one. For example, the source of M3 is drain of M1, source of M4 is drain of M2, and we are interested in this voltage at the end. Why we are interested in D4? Because that is the VO minimum, so we want to know what is that minimum, okay. In most cases the source body is grounded and not connected to source, okay. They are generally grounded, okay. But there are technologies in which it is connected as well, okay. So different than VSB's effects could be taken care in case this is not connected directly but to a ground. If it is a ground, that means there is a potential there and some VT will move, okay. So that part will be there, but right now I am not considering VSB effect, but they can always be brought into the expressions. Maybe I will give an example when I brought that expression. Is that okay? So let us see, first thing I am worried about is the V minimum part, because R out by intuition I know, because I have put a cascode I am going to get it higher, but I want to know what is the, of course I may calculate that as well, but first let us see what is the V minimum. Let us say for the values given by Boyce book, VGS is 1.2, let us say there are two batteries, one is biasing this and one is biasing this. We could say there that VGG1, which is same as VGG2, this is coming from the mirror side. Please remember this value is coming from the actual reference side. So it is equivalently saying there is a bias to M2. Please remember VGS2 is same as VGS1, okay. So I am just writing directly there. So VGG1 is VGG2, which is 1.2 volt, because VGS has been given to me 1.2 volt. Similarly VGG3 is equal to VGG4 from the other side. Please remember all that I am doing this and this and this, okay. So this is equivalently saying a supply coming here, so which is 1.2 here plus 1.2 here for that VGS, so it is 2.4 there. So for M4 to be in saturation, what is the condition M4 will be always in saturation? The VDS4 of M4 should be larger than VGS minus VT for M4, is that correct? That is the condition which it should satisfy if M4 to remain in saturation. Now we also know VD2 which is equal to the VS4, that is the source of M4 is same as VD2. If M2 is to saturate, the VDS2 or VD2 of this should be larger than VGS minus VT of this. Two transistors should remain in saturation so that the output resistance will act like a cascade structure and you will have mirror transmission anyway, otherwise, because this will be same as the other side current. So if these are the two conditions and if we keep VDS2 and that is the condition we want to force, what is the minimum VDS2 I should have? Okay. If this VDS2 is same as VGS2, so VGS2 minus VT will be always smaller than VDS2. So transistor will always remain in saturation if this voltage is same as this voltage. That is the minimum value of VD2 which allow transistor to saturate. Is this equal to this? If they are equal, then transistor M2 will always remain in saturation. Is that correct? VGS minus VT will be always smaller than VDS. This value is going to vary with the difference of currents which I will pass through that. This is a function of, someone yesterday was asking, so I am proving it. Yeah, that may vary, but up to which I will allow it to vary. The minimum value which I should allow is VGS minus VT should be smaller than VDS, will only occur when VGS is same as VT. Is that correct? So if that I am calculating what is the minimum, I am not saying at VOV, I am calculating what is the minimum possible available to me. So if M2 remains saturation with VDS2 equal to VGS2, so VDS2 is VGG1 equal to VG2 is 1.2. So if I keep it 1.2 volt, I am guaranteeing M2 will always remain in saturation. I am actually interested to know what is this value. Just a minute, because I want to see that upper value also should saturate the upper one. So I am trying to see both together how much I will saturate. Okay, is that okay? For M4 to be saturation, VD4 minus VD2 should be greater than VGG4 minus VD2 minus VT. That is VGS, which is VGG4 minus VD2 is VGS minus VT, and this is VD4 minus VD2 is VDS for this. This condition gives me, it should be 2.4 minus 0.83, substitute the values, so around 1.57, so it is 2 VOV plus VT. Now this value has now come, that unless I have a VOV which is equal to 2 VOV VT, I cannot ensure you now both individually VOV is sufficient, but together in series I must attain this value so that the output for which I am now calculating both transistors remain in saturation. So that the minimum I am now getting is 2 VOV plus VT, where it will definitely gap, otherwise you should have to further increase if you want 100% guarantee on it. But what is the, since VOV is 0.37 as you said, so 0.37 into is 0.74 plus 0.83, so it is roughly 1.57 volt which is required at the output. Is that correct? As the minimum Vmin. So that means it is not really doing fantastic job, because till 1.57 volt it is not acting like a good current source. That is the limit of this. But what is the advantage I got it? This I have achieved it, okay, I have figured out that, okay, what is the value I would prefer? It should be independent of VOV in such. Why should I feel it should be independent of VOV? Because if it is only VT dependent, then I am controlling it, okay. So I would like to have a current source which is only strongly dependent on VD and nothing else, no W bias thing. If I get that value, I am happy. So I am trying to reach towards that. But if I use cascade, I have a larger VD4 requirements, I am coming to keep M2, M4 in saturation. Now this is an issue which has to be tackled, because what is a good current source? In some cases maybe you have sufficient voltage margin, so you can still go ahead and work with it, okay. But in other cases this may not be accepted, you will actually prefer 0.8 or 0.7 volt as the Vmin for you. Now this calculations are all this to do how much minimum really I can achieve for you. Okay, is that okay? Now I can do without going into details, but as we have already done it, we can do for RO calculation by putting GMVA4 this, RO4 parallel, GMVGS2 both are in, as you said, you are in saturation. So these are equivalent circuit. I apply a Vx source, pass a Ix current. Why VGS2 is 0 I said? Because the source is coming from reference and that I must actually create it to 0, no current in the reference, all sources, current sources be opened and voltage sources be shorted. So the other side of circuit is not necessary because there I am forcing VGS2 to go to 0. Now if I do this, you can see GM VGS2 also will go away. So if I calculate this value GM VGS4 multiplied by parallel combination this, so R out will come, which we did earlier, is GM4 RO2 RO4, which is essentially gain times the RO. If ROs are equal, then you can say GM RO square, is that correct? What is the output resistance of a cascode? GM RO square. So we will achieve higher output resistance by simply cascoding. At what cost I did this? I had to have 1.57 Vmin for this current source to operate as a good current source, is that clear? So the conditions which I thought we can achieve by just cascoding was not sufficient, is that point clear, Pratik, Arik? I have improved RO, but I also saw it has increased the Vmin, which as I said, my first characteristics, ideally I want Vmin to be close to 0 or very sharp rise, very small Vmin, then it is a good current source. I am trying to reach that. So why are we looking into this? To reach there, we will one by one go step ahead. So I say okay, first we went for simple, then we say okay, let us cascode. So I brought R out higher. I now want to keep this output stay similar because I do not want to reduce my RO. If possible I may want to increase it further, but I want to now reduce Vmin. So what should I do so that I can reduce Vmins? Okay. Now what we do is we can reduce the Vmin by very funny circuit is done. This is called magic battery solution. This solution is named as magic battery solution. Okay. The rest part is similar except that, please do not worry too much, circuit is same as what it was, except that between the gates of M3 and M4 I have applied a small battery of Vt, okay, and that is why it was called. Of course there are number of variations on this, I am giving you the simplest of them. There are 4 such circuits which can do similar things, okay, one of them maybe we will see. So what is now happening is, we have this 2 VOB by Vt which we are getting minus VOB Vt because this additional Vt we are supplying now, which will get subtracted. So now you are getting VOV as your Vmin. So you are reduced from 2 VOV plus Vt to only VOV, okay, which is what you said smaller. So I am putting a battery to compensate, I will be able to reduce my Vmin, but no cost at output because our cascode stage is not changed by me, is that correct? Now maybe you look into the book, there are a variety of course this name is not given by Baker, but this is an interesting name I read somewhere, it is called magic battery solutions, okay. How to create this Vt is what the solutions are, different way you can create Vts and then you can see that you can compensate for, please remember this is opposite sign, that is why it is deducting actually. This technique of readjusting the V minimum by adjusting additional batteries, you can have multiple, there are multiple systems. So maybe you look into book, this is just to give an idea how Vmin can further be reduced. Normally batteries are not put like this, so some other method we will use to put V minimum Vt there, equivalent source, okay, equivalent reference. So I need a voltage reference there. So now we must look for voltage difference because I need that somewhere here to get it, okay. But as far as theory is concerned, if I can put some value there, I can minimize this value, is that okay? Yes. If you change the VGS, okay, correspondingly this voltage plus this voltage, this 2 VOV minus this, if you subtract, then the VDS will be this to this will be this. Try yourself, substitute the values. Okay. For every node, okay, the method I suggest you, every node you calculate voltages and find voltage here and find voltage there. VDS of M2, but that additional, that will be same VDS, because that I cannot minimize, because that will decide by my current which I will push, but at least here it was VOV plus VT, that VT I have actually cancelled. Your point is very, sorry, I think you are also right. This value which I have reduced, here it was VOV plus VT, that I have actually reduced by 1 VT by putting a battery, is that correct? So overall 1 VT reduction I have done. This is just, you can see 1 VT only I am reducing out of it. That VGS I have subtracted 1 VT. I can readjust this value to some further reductions, but the problem is if I reduce this too much, this transistor may not remain in saturation. So how much VT to adjust, or how much battery to adjust is forced by me M2 to remain in saturation. So this is what I thought, that this is good enough, and that is the minimum I should start with. Okay. So at least 1 VT V minimum I have gone down. Okay. Is that okay? Sorry, I should not have said this. This is not, this is what you have said is correct. This is at VDS2 is the value which I got. Okay. Okay, we are very good. The another thing which is worrying me on any current source and current mirrors is something which is in real life no parameter remains constant, is that we have seen variability issue. So how do you monitor variability? What is the method of finding variability? So one method is called sensitivity analysis, is that clear? What is sensitivity? Here is a definition of sensitivity. I want to find variation of Y with reference to variation in X, is that okay? I want to find sensitivity of Y with reference to variation in X. So it is defined as limit of X to 0 delta Y by Y upon delta X by X. This is the definition of sensitivity of Y. Okay. If this is my sensitivity, for more details please read Boyce and Baker's book. If I have missed something, you actually look for other circuits there. Okay. Because I do not want to spend all of my time in only current sources. I have limited time, so I only showed you the method what they are trying, and that is what we are looking for. So let us look for the sensitivity of current source with respect to which parameter is the first parameter I should look into, the power supply, because power supply is never a constant quantity. It is externally connected from the pad, and that can vary because of variety of reasons. Particularly in op-amp we actually look for that variation. In what term we call there? Power supply rejection ratio. If there is a variation in VDD, what happens? Okay. Here there is no PSRR, but we just want to know what is it. Let us say for a simple mirror I calculate my sensitivity. Okay. Since IDS1 is equal to IDS2 if W by Ls are equal, then I0 is IDS2 which is equal to IDS1. Okay. But how much is IDS1 we have calculated? VD minus VSS minus VGS. Please remember where drop across this plus drop across this plus VSS is essentially net VDD, is that correct? IR plus VGS plus VSS is VDD. Okay. So I can evaluate IDS1 from that, VDD minus VSS, of course this is minus of minus, so it will add minus VGS upon R. Now we want to find the sensitivity of I0 because that is my output with reference to variation in power supply voltage. So I define it as limit of VDD tends to 0, very small value, delta I0 by I0 delta VDD, sorry. Sorry, I made a mistake everywhere, please check it, you are very good. Okay, so this, if I rewrite this, this is equal to VDD by I0, partial derivative of I0 to VDD. So it is, this is my SI0 VDD is VDD by I0 delta I0 by VDD. But if I see delta I0 by VDD from this term, which is delta IDS1 by delta VDD, if I differentiate this equation of IDS1, I get 1 upon R, is that correct? So if I get 1 upon R, because these are constant, so I leave them. Delta I0 by I0, if we look at it, I substitute some values, but okay, first let us look at this. This is VDD0 by I0R, and the value which I last time used probably is the R is 380K for a 5-volt supply. 5-volt means 2.5 VDD and 2 minus 2.5 VSS is net 5, is that clear? 2.5 VDD and minus 2.5 VSS, so sum total is, but here only VDD I am looking, VSS I am still keeping constant, okay. So 2.5 upon 10 to the power minus 5 into 380, I0 is let us say 10 microamp current. Assumption is I0 in our case example is 10 microamp current, that is what we solved the problem. So this is what it is. So this gives me a sensitivity of 0.66. If I want to know the change in current of I0, then 0.66, 0.2 upon 2.5, which means if VDD has change of 0.1 volt plus minus 0.1 volt, this is the kind of percentage variations you can get in I0, is that clear? So this is the sensitivity what I0 will change if VDD changes, is that correct? This is essentially why we are looking this, because we constantly say I want constant current source, okay. Now this constant word is how much constant, okay. So what should be the idea here, whether the sensitivity should be larger or smaller? As small as possible, because I do not want current to change with change in VDD or very small change in I0 with reference to large change in VDD. If that happens, I say I have closer to my constancy of current, okay, at least from the power supply side, okay. If that influences directly, I change 1%, I get 1%, 10% also, then I have a worry. So at least it should not be, it is less than 1 anyway. So at least you have improved a bit by this kind of sourcing you did, okay. So this is one parameter. Which is the other parameter we should worry about in variations? One is power supply value. What else? When the circuit is working somewhere, what is it changes? Because current is flowing, temperature. So the next worry is temperature variation, okay. Is that okay, Surbhi? The first is power supply voltage variation, the other is temperature variation, and temperature variation is many times much stronger in fact, okay, because device is normally operate from where to where, in many operations as much as minus 25 to 150 or 125, okay, or minus 40 to some 105 degrees. This is military standards. So device may even in ambience may vary in its own temperatures, or device during working I square R loss will keep heating the device unless you dissipate it properly. So the temperature variation is a crucial fact for us to figure out whether I0 will change at different temperature. What do we expect? Should not change, that is what I ideally will like. The temperature variation sensitivity is expressed as temperature coefficient, is defined as temperature coefficient, okay. Sometimes they write like this, so maybe I will write like this, okay. TC is capital, F is subscript, so TCF, temperature coefficient of I0, is defined as 1 upon I0 delta I0 by delta T, okay. This is how temperature coefficient of I0 will be defined. We already have written sensitivity of I0 to temperature, if we can find out, so it will be, okay, I same mistake again. Limit of delta T tends to 0, delta I0 by I0 delta T by T, T by I0 delta I0 by T. So you can see from here there is a relationship between sensitivity and TCF, is that clear? This part 1 upon I0 delta I0 by dt is nothing but TCF of I0. Please look at it, TCF of I0 is 1 upon I0 di0 by dt. In differentiating this I get 1 upon I0 di by 0 multiplied to T. So T times the temperature coefficient, okay, if I put F of I0 is sensitivity. So if you have been given sensitivity and temperature of operation, I am actually specifying temperature coefficients. Is that clear? Is that clear? or vice versa. So again same thing, data is given in some cases in S form, some cases in TCF form, but both are anyway interrelated. Okay, let us calculate TCF. What is I0? As just we wrote, will be, is it okay? So far so good. I0 is IDS1, which is VDD minus VGS minus VSS by R for the simple mirror. I differentiate. So it is delta IDS1 by delta T, and I differentiate this term with reference to temperature. Now which are the terms which are functions of temperature? We assume VDD and VSS do not change with temperature, okay. This is also not very valid statement every time, but assume it right now. But mostly yeah, you can assume that. But which is the strongest function of this temperature? The resistance, which has a direct change in resistance occurs with the temperature. But Vg also changes because Vgs has something to do with Vts, okay, which we have VOV plus Vt. So obviously I must look for VGS variation with temperature, and I must look for resistance variation with temperature. So I differentiate this two terms, so 1 upon R dVGS by dt plus 1 upon R dVGS dR by dt. If I do this, then I get R to the 1 upon minus 1, oh minus 2 हो जाएगा, ठीक है, you are right, differentiate किया ना, okay. So I then substitute this 1 upon I0 TC I0, and if I whatever just verify properly 1 upon dV by dt minus this dr. Okay, so I now substitute VGS, is that correct? What is VGS? VGS is equal to Vt under root 2 beta I, okay, or sorry I by beta. If I do that, then I can actually look for this expression. Similarly this, just check, maybe as I say in adding I might have done some mischief, but just check it well. So basically what is TC or TCF, if we keep calculating the same name now everywhere, if you substitute for those values of simple mirror 380K and 1.2 volt VGS VT or 0.83 volts, we can substitute those value and we figure it out. This is 0.17% per degree centigrade, typical. But normally all TCs are expressed in what numbers? Not in number, they always express in part per million, okay, 1 in 10 to the power 6, that is the unit they normally use. So if you convert this into part per million, it is 1700 part per million per degree centigrade is the temperature coefficient of I0. By the way, 1700 is not a large value compared to other value which may be 3000 or sometimes 2400. So this value is not largest among the values which I will use in my analysis. Resistance, in fact you calculate, is typically around 3000 for the actual resistance I make in chip, okay. So it is largest variation comes from resistance. Further this comes from VT variations, okay. So we will see how much variation temperature dependent each has, how much ppm they have, okay. But this is to give an idea. Typically the source currents are 1000 to 1500 to 2000 ppm per degree centigrade rise is always seen with the temperature. So now you think of it, if I increase it by some amount of temperature, the current will correspondingly change proportionately, and are you really accepting that much change? If that is acceptable to you for your device circuit further, no problems. If you do not want that, then think of it to adjust these values. What should I do? You can see if I can somehow these two terms equal plus and minus, I can bring down that value, okay. That means I will design it something. But to design this, if I change my W bar or VGS or anything or VT, then what will I change? Whether that M2, M4 will remain in saturation, I am not guaranteed. So I must first go and verify every time there, okay. Because my R0 guarantee, I must ensure that R0 is higher. So by doing this, I must see that my other factors are not terribly disturbed, okay. And that is where the design starts, that how much TCF you can have to adjust what best RO you can get at what B minimum you can get, design whichever is possible, that is the source for you, is that correct? But In simple mirror RO is not very high, so we are anyway going to do cascade of that with battery, magic battery there, so that further reductions in Vmin I can attain, and also I have higher RO. But with that I have not done this, with that I must calculate now TCF Y0 and figure out whether it is lower or higher than 1700 for the simple mirror. If that is much higher, how much tolerance you have? Okay, verify yourself. If that happens, fine, otherwise go back and redesign everything. Okay, is that issue clear to you? Parameters I am worried about is saturation of M2 M4 to get my R out higher. I want V minimum, so I will use some other circuit part to reduce minimum, and doing all that with that W bias I used, I figured out my TCF is too high, then I will have to rechange everything. Okay, that is where the design starts. Given this value, how much tolerance I have? Okay, because designers do anything, at the end of chip it should follow you. So what it will give, you will have to model it back and say, oh, I did not take care of TCF, therefore these values are gone out. Okay, so this such a situation you must take in designs. Okay, just for the heck of it, I just give some values for you to see what are this. Typically a resistance which is used in diffusion N plus region of source drain, whatever you use in a MOS transistor. If I make a resistor out of N plus region, how do I make a resistance of N plus region? Anyone? Maybe I will show you quickly. This is my N plus area, okay. This is my junction depth in P, okay. This is the source drain length, what we call LS or LD, whatever it is, and if you see it another dimension which is W, okay. This is my W. So the area is W into Ls, thickness is Xj, so and if the resistivity of this sigma is Q mu N plus, so I know rho which is 1 upon Q mu N plus, mu N is known, N plus is known, R is rho, that is rho L by A, T of course, rho T by A. So I can calculate the length of the source region. Do not use source as a source in the transistor, as use another, say for example the resistors are made something like this. This is your transistor for example, this another N plus region is created here, okay, and the resistor is built in that. That is how ICs are made. Whichever component you want, you should put another region for that. What is the problem with such putting there? What is the criteria I should have? This is N plus, this is N plus, this is N plus, but this is P. Isolate. How to isolate the two areas? This either put an oxide down here which is STI, or this NPN transistor should have a gain of less than 1, okay. Is that clear? Or put even higher doping here, okay, so that the gain goes down, okay. It is called guard ring, okay. So put either a guard ring or put a isolating oxides below, trench it down and separate the two areas, okay. That is the basic requirement to make any other component. So every component in a circuit has to be isolated from the others by either of these techniques, okay, and that costs hell of money, okay. Yes. This is a resistance ना, एक bar of semiconductor है, length, width and thickness, so rho by A. So I adjust on the lengths and width is given by W which is given to us. So I have a longer N region, or this decides my resistance. Typically even this is not done because N plus is not a constant quantity, so it is actually given by R is equal to Rs L by A, L by W. Rs is called the sheet resistance of the N plus region, which is typically maybe 10 ohm per square or 15 ohm per square or sometimes even 1 ohm per square in some areas. So Rs is known to me from technology. W is generally used as the standard widths, and the lengths are only adjusted to get your sheet proportion to that sheet any R you want, okay. Is that okay? This is how all resistances are made, okay. Which is the higher resistance if I want, what should I use, which area I should use? N plus is a very low resistance because N plus is a higher dope region, so conductivity is higher. So what should I, which area I should use? P region. So actually I have another this separation, and this P region I have another P created in the P, which is the dope sheet resistance of my choice, and then make a contact here to make a higher resistances. Is that clear? I have P region created in the P well itself, okay, and make two contacts separated by length L to give my sheet resistance into L by W values. Why I said P? P will have a higher resistivity and therefore higher sheet resistance. How can I reduce, increase or decrease sheet resistance other than this? What is sheet resistance I defined? Anyone? Rho by T, thickness. I can adjust even thickness, but normally I cannot separately implant something here and separately implant. If I already doing implant, I will open a window and implant right there, okay. But the higher resistance I will have to implant anyway, okay. So for a lower resistance, the source area, the drain area, whatever N plus I am doping, same I will use it for low resistance values. I will only adjust lengths for them and widths of course standards, so I will get my resistance of that. But if I want higher, I can even do better. I can deposit, anyway I am going to have a poly here, so I can have a poly layer, okay. Of course it has to be also protected by oxide, and I can make a contact to poly because poly has a very high resistance relative to everyone else, okay. Is that clear? Another mask, please remember what is the worry in technology. Everything I do individually, I will require every other area to be masked to do process there. एक मास्क $1 million खर्चा है, okay. So now do you really wish to do that? Because how much money है वही करोगे ना. So everything is not. वैसे how do I make capacitors in this technology? I have a MOS na, mass capacitor sitting there, okay. But there are other capacitive methods also. You can also have a transistor and ground it both sides. This is a good capacitor. If I connect gate to the source, I will make a diode out of it, okay. I showed you earlier diode connections. So I don't make any additional device in the ICs, I only convert my MOS technology areas into variety of components. What I cannot do then? Resistor I did, capacitor I did, diode I did, inductance. Inductance is nothing I can do about. All that I can do a print a spiral on the top of this, okay, and that is very difficult game, you know. I will show you some. It takes so much of area, make a small inductance, 0.1 nano Henry will still require some 20 turns or 18 turns, okay. And that area, if you see a RF circuit, 90% of RF circuit area is because of the inductances, okay. In analog chip, except for VCO where we will actually go to inductance, we will never use inductance anywhere, okay. Even in filters, which we will do possibly, I will replace L by something, okay, okay. By using switch capacitor, I will use LC as combination and every L I will replace as by C, okay. So I will never use inductances as far as possible in analog, okay. I will only use capacitors, I will use resistors also out of the same, and I will use MOS transistor, nothing more or nothing less, okay. That is how the integration is possible. So please do not think that even if I show you this, essentially what I am going to do is the following. A P device properly biased, it acts like a resistor, okay. So I am not actually going to use any time a resistance anywhere. Is that clear to you? So please take it that in real life on a chip only MOS transistors are preferred everywhere. Convert as much as you can, okay. इसको ground करो, इसको ground करो, इसको खोलो, इसको जो भी करो, but that's all that I will give you, okay. So this has to be understood that in IC technology the reason is size. W by L I want to see smaller, any other way I go it will be larger. So it will not be as good. So what is the problem? The sheet resistance, I am sorry, the TCF of this and TCF of this is different in sign, okay, and that is the problem starts, okay. Then should we not really put a resistor to compensate? So that is what band gap reference people do, they actually put a resistance to compensate, okay. They do not put MOS device or any other device to compensate, they actually use a resistor because it has the opposite sign of TCF, so you want to subtract, okay. So please remember different components have different way of looking at it in a given circuit. This is some additional examples I gave you. Okay, so for the given n plus region, coming back to where I was, TCF R is 1 upon R dr by dt, which typically for n plus region is 2000 part per million per degree centigrade. TCF for threshold, I think this value you must be aware of, those who have done second year course. It is change in threshold voltage with temperature is typically 2.4 millivolt per degree centigrade with a minus sign, that is decreases in fact. So for a typical 0.83 value of this, TCF becomes roughly minus 3000 ppm per degree centigrade, typical. As I say, please remember in TCF 1 upon Vt is the value coming, so for this value will be function of Vt itself, which Vt you are using, is that okay? What is TCF of Vt? 1 upon Vt delta Vt by delta T. So 1 upon Vt has the value which you have to at different Vt, this will be large. So smaller Vt what will happen? TCF will be even larger, is that clear? Minus larger, okay. But this is around 0.8 volt Vts, this 3000 to 3500 is typically a ppm per degree centigrade is TCF. For a MOSFET, how much is this in the bipolar Raj? Delta Vb by delta T, there we calculate how much base emitter voltage changes with temperature. 23 millivolt, 2.3 millivolt per degree centigrade, similar numbers, not exactly same number, okay. वहाँ भी हमने thermal calculations किए थे, that's the way similar things are there. For a MOSFET, beta dash is mu Cox. So if I see mobility variation in this, it can be written as beta dash 0 T by T 0 to the power minus 3 by 2. This is temperature dependence of mobility. This gives 1 upon beta dash delta base roughly equal to minus 1.5 by T, where T here is in kelvins. So typically TCF for beta dash for the values which I used could be around 5000 part per million, very large TCF for these devices, beta dash. So you have seen, yesterday you were saying that beta dash has a very strong temperature dependence. Please remember this is for the Boyce-Baker's books data, based on that calculations have been done. For different values you will have to figure out actual values there. So don't say sir आपने बोला, ऐसा नहीं है, ये एक typical values हैं. Expression remains same, data you substitute. Of course 5000 will not become 25,000 any day, it may become 5,500, 4,500, but it may not be 5,000 for all cases we handle, okay. Okay, now we have seen sensitivity due to power supply and sensitivity due to this. So now when I am designing a current source, all these areas are in my mind. How much current I want, how minimum voltage I want, how much RO I want, and how much is the sensitivity or both for VDD and temperature I have. Based on that only my design will be a good current source, is that clear? Okay, here is another current source which slightly improves some of them, not necessarily all of them. We know the variation occurs. How do you get rid of variations in normal circuits? Word is not, I mean you are right, word compensation, but what do we really do actually? Feedback, negative feedback stabilizes everything, okay. So one technique of improving this is to actually use negative feedback. एक बढ़ा तो feedback से उसको दूसरे को फिर नीचे कर सके. That's what the negative feedbacks do, okay. So based on negative feedback and a simple current mirror, probably we can improve some of the sensitivity issues, and two such most popular current mirrors which are available, one is called Wilson mirror, the other is called regulated cascode. Okay. Both uses negative feedback in their circuits. Okay. Just now I said it, and now here that circuit. This R has been replaced by a P channel device. Now the question which you should ask, what is this V bias? Okay, this value, you know that M1 must remain in saturation so that resistance is constant. So how do you fix V bias? So you need voltage reference which is constant and actually used to connect there. Okay, I repeat what I say, I need a constant voltage source which I can connect here. Okay. So I will also see after the current source, I will also try to see what is voltage references available, and how to constants I will see their sensitivity with temperature in specific and value with the power supply variations. So if they are constant, I can connect them here, that value will push a fixed amount of half of this, and will flow a current of my choice through M1 and therefore M2. Is that okay? So V bias as of now I say it is constant. Okay. How do I get that constant is also in game. Okay. So we will see, of course there are another way of doing it, instead of actually doing it you can use a feedback also to keep V bias constant. So we will use some tricks there also. उसको बोलते हैं स्टार्ट सर्किट लगता है उसके लिए CFPM. सो एक इनिशियल स्टार्ट नहीं होता है तो एक स्टार्ट करते हैं, उससे फिर वो फीडबैक में V फिक्स कर देता है, and then it doesn't work itself. So we'll see that CFFP क्या है, that is another fun. Okay, here is Wilson mirror. What Wilson did over the cascode area, he did not change anything on the simple reference side. Okay. However, he has a cascode on the output side because RO you do not want to reduce. So, okay, I kept this series like this, but what I did is the output of the first this stage or M2 drain I connected to the gate of M4. Now let us see how it feedbacks. Please, have you drawn this figure? Rest you do not write, think only first here. Just draw the circuit and let us discuss first. Okay, so start looking. I right now assume because of my fixed bias, this current which need not be called IDS1, may be called I reference, whichever book sometimes says, is constant. Is that clear? IDS1 is a constant current generated because V bias is fixed by me, okay, and no variations are, I have taken care of all of it as if this current is constant. Is that clear? Now let us say for some reason I0 increases. Okay. If you say this current increases, what will happen? That means this voltage drop will increase, which means this current will increase. If this current increases, what will increase? This current will increase because the mirror part of that. If this current increases and this is constant, this voltage must go down, okay, because you are pushing on the top and now you are asking it to increase. So this voltage must go down. If this voltage goes down, VGS4 goes down. So I0 reduces, okay. If it goes too low, the opposite will occur, this will push till both sides match. So this is what essentially negative feedback does. Is that clear? And since negative feedback allows you to stabilize, which is the standard way of stabilizing anything, you can use a partially cascoded mirror using Wilson current mirrors, Wilson connections, and say that it will be much better than normal cascode sources. Is that clear to you? You did not get it. IDS1 is constant, but by force you are trying to change IDS2. Is coming from mirror from M3 side. इसका VGS चेंज किया तो उसका भी VGS चेंज हो जाएगा, गेट कनेक्टेड है दोनों के. What we are saying is How can it happen? No, it will not, and that is why feedback is, how feedback will push that same current is what I am telling. Is that point clear to you? Your idea is in a circuit two currents cannot flow, that is exactly I am also saying. Is that clear to you? Because two currents cannot flow, but now I am forcing this to increase, which means this voltage must go down because IR drop will go down, so that this VGS falls. So this current will reduce then. Is that correct? Because we say IDS1 has to be IDS2. Is that clear? So how a feedback will force that issue that IDS1 only current can flow down even if there is a variation in I0 is what I said, and therefore I0 will become constant independent of anything. This is called Wilson's feedback system. These are simple statements, nothing very great. Current mirror has I0 much stable than the simple mirrors. Output impedance is further improved because of the cascade connections. Okay. I already said, for those I have made a statement, the V bias is normally taken for a stable band gap reference, okay, which we will look into. Okay. Can you think why there also it is a constant? Must be there also should be feedback, because otherwise it cannot create a constant value. So if band gap reference must have some comparisons, it must find errors and feed it back, so that it reaches to a constant value. Okay. So we will see that later. Is that okay everyone? This is VGS2, this is VGS3. Okay. Now we see this is VGS4, this is VDS4, this is okay. What we said, as far as the P channel device is concerned, it is only now acting like a current source with a resistance of RO1, and that is a constant current source, because you say V bias is fixed. So we do, in AC we do not consider that, that is a fixed source. Okay. But this RO1 will appear for that, because there is the output resistance of that P channel device. Okay. So as far as I am concerned, for the first transistor only RO1 from drain to source is available, so I have plotted it here. Okay. For the D2, for this VGS2, by the way what I am calculating, I am giving a Vx here and finding Vx by Ix to get R out. I am not doing anything, I have already shown you here. I am trying to find R out from substituting, putting a Vx source and finding Ix there. On the transistor D2 it is RO2 shunted by GM2 VGS2, but this D2 is gate of M4. Is that clear? Please check it. D2 or D1 is G4. Physically connect किया है ना हमने. So this D1, D2, G4 are same connections. D1, D2, G4 are same connections. Is that okay? This terminal and this terminal are same. So this is that line. Okay, three of them, D1, D2, G4. Now you see there is a VG here coming here, which is same as A voltage, minus the source voltage of M4 is the VGS4. Is that correct? So the S of this transistor M4 and the voltage here subtraction is VGS4. So this is my gate, this is my source. The gap voltage drop between gate and source for 4 is VGS4. Sign please check it. This has to be plus because this is an N-channel device. So this is plus and this is minus for S4. Is that okay? Is that okay? So this VGS4, why I have drawn this circuit is this, you should also see that the way I see a circuit I can make an equivalent right there. And then I will say okay जो shunt है वो नीचे ऊपर कर देंगे, but basic idea is just to substitute whatever you are looking for making an equivalent. My suggestion to you is this method is always correct, okay, because you are only following node and from there whatever you are seeing you are substituting there. The S2 and S3 are same, which are grounded. S2, S3, source of M2, M3 are connected and grounded. S2, S3 are connected and grounded. Okay. Now I have to see drain of 4, this So this is my where I am actually going to push the Vx Ix currents, Vx source and Ix base, which is my I0 which I am looking for. For this transistor, what is the current source? GM4 VGS4 shunted by RO4. Just wait for this. If I say, and just now someone was asking, if the source is bulk is grounded, between source and this there is a voltage now VSB, is that correct? However, the way VSB I can see, VSB4 is nothing but the signs I am putting plus minus for a source, which is essentially equal to VGS2 and VGS3. VGS1, VGS2, VGS3, because they are connected with this, is same as this potential. So I say VSB4 is nothing but VGS2 or VGS3, is that correct? So this voltage, so this is my S3, this is my S4, this is VGS2 which is equal to VSB4, and since please remember this is VSB, opposite polarity, current pushes up GMB4 VSB4, okay. Now this is the equivalent for this. For M3, is GM term will appear there, because this is a diode connection, so only RO3 parallel GM3, I kept it RO3, you can even neglect RO3 because GM3 will always larger than 1 upon RO, therefore that, but right now I kept it, I always say I let it because I do not know what currents you are going to use, so I want to retain them in case they are comparable, make it parallel. Okay. Now this is very big circuit looking, but there is nothing big part in that. The first thing I calculate is VSB4. Okay. VSB4 is VGS2, same node, VGS3. Now look at the current which is passing through this. This drop is VSB4. Is that correct? Drop across RO3 parallel GM3, and what is the current flowing? Sum total of these three, whatever current in this is essentially the net current. So current coming out is also Ix. एक करंट है, तीन पार्ट में डिवाइड हुआ पर नीचे आके फिर सम हो गया, तो ये सम करंट पर यहाँ आ गया, इधर तो खुला है so no current. So all this Ix current flow through RO3 parallel 1 upon GM3, is that correct? That is your VSB4. So I get VSB4 is VGS2 equal to VGS3 is Ix times RO3 parallel this. Now I want to calculate VGS4. How much is VGS4? If I know this voltage and if I know this voltage, is that point clear? How do I calculate VGS4? This voltage minus this voltage, is that correct? That is my VGS4. So I write, how much is this voltage? GM2 VGS2 parallel combination of RO1 and RO2, is that correct? So this is my voltage here, is that should be clear? The voltage drop across parallel combination of RO1 RO2 is nothing but the voltage across this, that is VG4. How much is VS4? The VGS2, just now you wrote that, okay. Please remember this voltage is this voltage, so you subtract this, is that clear? So you get VGS4 is minus GM2 VG, this minus VGS2 is your VSB4, okay. But what is VGS4? Now why I am interested in VGS4? Because I want to find drop across because of this, so I want this current source, is that okay? Everyone please write down, this circuit is, as I say, you can simplify circuit by parts and can directly write many things, please do not write because this gives you actual features what is happening there, is that correct? Not only for this circuit, for any circuit, if you are more than one transistor on the top, please put 3 layers of them, okay, and actually match the nodes correctly, okay. That will never make any mistake in evaluations at the end, okay. So this is, I am not saying this is the method, but this is much simpler method of doing things. I am saying this from my experience, but you can do much better, you can simplify circuits much equivalent of what is the other method? For each stage find equivalent Thevenin source and Thevenin resistor replace there, keep doing that, that also is a equally good method. But in doing that essentially you are partly doing the same thing which I am doing, I am doing all together, that is it, is that correct? So my method is no different from the other methods given in the books, it is same, I am only trying to see, visualize what this circuit is doing, so I actually show you what is the equivalent of that from there. Please do not think it this is the technique or something, okay. Before we quit, let us finish this today. VSB4 is the between the source, because please remember there is a drop here which is the source voltage for D4, M4. Since substrate is grounded, there is a VSB4, is that correct? But I know this VSB4 is same as, because this is the same terminal source here, must be same as this and this. SB4, this is plus and this is ground, is that sign correct? Source is at higher potential than the ground, okay. So that is the way, that is why I said the way I had drawn, I am only keeping signs accordingly. What will happen, and that is why actually I changed this sign also upwards, okay. Okay, is that now clear to all? Okay. So VGS4 is therefore equal to minus, I take sign, 1 plus GM2 RO1 parallel into VGS, just combine, nothing very serious. But VGS2 is VSB4, I just wrote, so I replace VGS2 by VSB4, but VSB4 I already calculate as IX parallel multiplied by RO3 parallel 1 upon GM3, so I substitute that here. So I get VGS4 is equal to minus 1 plus GM2 RO1 parallel RO2 into IX RO3 parallel 1 upon GM3, is that okay? So one equation I figured out in which VGS4 is related to this, okay. If you look at the circuit once again, please write down this, we will come back to circuit again. Only up to equation 1 you check and then I will draw the circuit, okay, is that okay? Everyone wrote down this equation? Okay, see the circuit, this IX is divided into 3 currents, is that correct? GM VGS4 minus GMB VSB4 plus Vx divided by Vx minus VGS2 or VSB4 by R0. This voltage minus this voltage divided by R4, this current source and opposite current source, this is the net current which is Ix, is that okay? 3 parts, each is, this Ix is sum total of these 3, okay, because you can see below Ix is coming, so all 3 must be summed up, proper signs. So I summed it, GM4 VGS4 minus GMB VS4 plus Vx minus VGS2, is that correct? VGS2 divided by RO4 is the second equation. Then I use these 2 equations and evaluated Vx by wherever this VGS4 is there, I substitute all of it here, collected the terms for Ix, collected terms for Vx and then divided Vx by Ix. Okay, so just check, this is RO, so this is RO, I do not know which one, but just check, some RO must appear there, अंदर होगा, okay. No यार, ये तो GM RO, okay gain, so यहाँ कुछ RO होगा, ठीक है. Okay, so check it. All that I say, what I did in the paper, I actually substituted VGS4 here, VSB4 in terms of Ix again, and then I collected Vx and Ix terms and divided. This is what I did, so this is what I got. चला ये last expression check कर लेना. Okay, please check it, sorry for my mistake. I should do, but anyway maybe tomorrow I will actually show you correct expression which I got. In normal cases GM3 will be same as GM4 because I will keep M3 M4 identical, thresholds are same. RO3 parallel 1 upon GM3 I will replace it by 1 upon GM3 because I know ROs are larger, okay, and GM3 is equal to GM4, so I will say RO3 parallel 1 upon GM3 is 1 upon GM3 or 1 upon GM4, and I call them GM itself per se, okay, I can use that. I will also say RO1 is equal to RO2 equal to RO4, all these mirrors are same, so all ROs are 8. If I do all this at the end of the day, and let us say GM2 and GM4 are only one, this can be adjusted. We say roughly R out will come RO plus GM2 RO square, okay, or roughly GM2 RO square, okay. Cascode, so nothing great, all that I did after all these huge calculations I arrived at saying that it is GM RO square, okay. No great this, but just to say that the circuit is larger, things do not change very much, all that you have to keep evaluating expression wise, longer expressions, okay. So do not get fear of that, okay. So obviously we knew it is a cascode and therefore it has to boost RO. Now VO minimum is the next thing we want to know. Okay, ma'am, you just write this final expression which is of relevance to you, you can do whatever you lay. R out is RO plus GM2 RO square. By cascode the output impedance has boosted, gain times RO, okay, GM RO is the gain, so times RO, that is the boosting of that. Further boosting how can we do? You can use cascode with a gain, okay, so you can further boost RO in case you need further R out higher, some other penalty of power and area you may give, okay. Okay, what is VO minimum? VD4, okay. At the end what I wrote is otherwise also true, so I did not bother to see up, I say it should be RO plus GM RO square, okay, equivalently. If you see this figure, this voltage is this voltage plus VGS, I repeat, this is VGS, you have come here plus VDS, is that correct? I repeat again, this voltage is same as you reach here, this plus VDS of this is the VD4, is that okay? So VGS3 plus VDS4 is the output voltage V0. So VO is VGS3 plus VDS4 sat, the transistor must remain in saturation. So we say it is, what is the age of saturation minimum ke liye? VGS minus VT. So you substitute VGS4 minus VT4. I can rewrite now VGS, how do I write VGS in what terms? VT plus under root 2I by beta plus, have you written down this? Okay. So we write VO minimum is under root 2I0 by beta 3 plus VT3 plus 2I0 by B, एक VT cancel कर दिया मैंने, okay. If betas are also equal, which you can, then एक 2 और आ गया बाहर, 2 into 2I0 beta dash W by L plus VT. So now VO minimum is proportional to 2I0, under root of 2I0. So larger the current source you are getting, by definition or by theory your VO min will increase, is that clear? This is not, you can't do much, okay. Essentially I am saying even if slopes VO minimum whatever you are getting, if this is your this, if you want higher currents you will have to, sorry, here you will have to do only this, there is no other way of pushing higher currents. If you push higher currents, drops will also increase. Essentially what I am saying, Ohm's law है, current बढ़ गया तो drop बढ़ जाता है, there is nothing I can do, only thing is it is not linear like Ohm's law, it is under root of I0 which is it proportional to, okay, because of the square law term I am getting, okay. So I can evaluate my VO min. How do I minimize this? I cannot change I0 because that is what I am looking for. all that I adjust is W by L's, okay. But if I adjust W by L, what will happen? The mirror current and reference current may not be same. So I will have to figure out what reference I should keep, so that with this W by L I get the I0 of my choice, okay. That you can always think. Is that clear? Because the ratio may not be same, then it will transfer in a ratio. So initial current must be boosted to come to this value if W by L is changed on the other side, okay. Figure it out what should be reference current, okay. That is how you will be able to define specifically this, okay. We will come next time what is we call VT reference current source.